you already have access to the information. I just wanted to give an overview of different topics. So today, I already mentioned what we are going to cover. The first 3 lectures would be mostly about preliminaries. So the second and third lecture would be about cryptographic preliminaries, hash functions, elliptic curve cryptography, zero-knowledge proofs. Then there would be a lab practice on also cryptographic preliminaries. So the students would be able to get some practical knowledge about the cryptographic technology. Topic number 4 would be an overview of the blockchain technology, its evolution, types, features, benefits, challenges, the architecture of blockchain, and what it means for different systems and applications. Then we'll finally take a deeper technical dive into Bitcoin. So lectures 5 and 6 would be all about Bitcoin and its features. We give it the credit because it was the first technology, the first cryptocurrency that created the hype. Then we have tutorial still about cryptographic primitives, in this case zero knowledge. Topic number 7 would be mostly again the background history of consensus research and over the last 40 years. So it will be mostly history, but I'll also briefly talk about the newest discoveries in this topic. So why are we given this background on cryptographic preliminaries and on consensus mechanism? Because blockchain is mostly a smart combination of different technologies. In order to understand blockchain, we need to know distributed systems, operating systems, storage systems, and security and cryptography. So the background is important. Lecture number 8 would be about creating more scalable solutions. So while blockchain provides a lot of benefits, it also has a challenge of scalability. It's known not to scale beyond certain limits. So, and people have been looking into ways to overcome that challenge. So lecture number 8 would be about different techniques to this end. Lecture number 9, and further on, we'll talk about different technologies related to blockchain other than Bitcoin. So after Bitcoin, there started a number of, there was significant interest in the technology, and a number of alternative solutions came, and we are going to take a deep dive into some of those solutions. So in lecture number 9, it would be Bitcoin NG and Algorand. So Bitcoin NG came from Cornell, while Algorand came from MIT. And today, most of the technologies actually originated from academia and later became practical currencies. Algorand is one of the top 10 currencies today. Then the next lecture would be about 2 additional blockchain systems, Stellar and Monero. Stellar came from Stanford. Monero is different in the sense that it's not came from academia. Monero has strong impact on privacy. It providing better privacy than Bitcoin. And in the next lecture, lecture number 11, we'll talk about even stronger privacy guarantees, systems with even stronger privacy guarantees, such as Zcash and the related technologies of Zcash snarks. And we'll talk about alternative mining. Then we'll have 2 lectures on Ethereum, where we'll talk about transactions, mining, and smart contracts. We'll also have 2 tutorials on Ethereum. So where you would learn how to work with the Ethereum tools. Then There would be a lecture about Hyperledger, which is not really a system. Hyperledger is an umbrella of different projects. Some of them complementing each other, some of them competing, some of them unrelated. So we'll take a look at the umbrella, and especially the flagship project within the umbrella called Fabric. What's uniting all those projects is that they're mostly oriented towards consortium blockchain as opposed to open blockchain. And in lecture number 4, we'll discuss the differences. Next lecture would be about Corda, which is yet another project within the Hyperledger umbrella, and about the Ripple system. And there would be a lab practice on Hyperledger blockchain as well. So most of the blockchain projects build a chain of blocks, or blockchain means a chain of blocks. So you can imagine a train where the blocks are connected. We'll be talking a lot about that structure. However, there are some more advanced systems which, instead of a linear chain, build a directed acyclic graph of blocks or transactions. And we are going to have 2 lectures dedicated to that topic. Then there will be a lecture about blockchain security, different attacks on blockchain, and different defense mechanisms. And there would be a another Ethereum-related tutorial. Next, Dr. Chirag Moody will talk about smart contracts and vulnerabilities and solutions in the context of smart contracts. And there would be 2 lectures dedicated to digital identity management, which is a very important topic today. So there is a trend that of self-sovereign identity. And self-sovereign identity means that the subject of the identity should be able to have control over where the identity-related information is stored and with whom it's shared. So not the, say, the government or the entity or the university which issues the diploma, but say the student who gets the diploma will decide where the diploma is stored and with whom it's shared. Of course, there are very interesting questions related to security and privacy of such a scheme. So we are going to have 2 lectures about that. Then there will be a tutorial I previously mentioned where I would demonstrate different blockchain-related tools we developed, a simulator, and also generator of synthetic workload. In the next topic, there would be, well, the rest of the course would be mostly about different use cases. There would be 1 topic on a use case for real estate and supply chain management. There would be two lectures about blockchain for smart grid. And there would be a tutorial with case studies on certificate chain, property chain, and yet another lecture would be on e-governance and remote voting. 1 lecture on the use of blockchain in healthcare, and yet another use case where blockchain is used for taxes and the legal documents. There would be a topic related to NFTs and metaverse. Another lecture would be on central bank digital currency, where there is a push to replace paper money in different countries with electronic funds, but still issued by the central bank. So the interaction with the central bank and individual vendors and also clients would be the main topic in that lecture. And finally, there is a lecture on blockchain-related storage, research-based development, and outlook for the future. So that is pretty much the structure of the course and the topics. If you have any questions, please feel free to ask. Okay. So before we get to it, I understand it may be a bit boring for the audience when the movie starts with credits rolling, but it's important to give credit when the credit is due. So most of the materials in this course is basically developed based on the courses I was given in different places. But originally, those courses started from a tutorial we as a team gave at the DEPS conference in 2018. And the tutorial is called Deconstructing Blockchain Concept Systems and Insights. And I'm grateful to all the authors of the tutorial, whose material I'm reusing in this course. And I'm also very grateful to Dr. Chirag Moody for additional supporting material, as well as many discussions and helpful suggestions about how to improve the material of the course. All right, then without further ado, let's give an overview of the technology. So, blockchain. There are so many people using the keyword of blockchain, and also journalists. There are not so many people who understand what the technology actually is and how it's working. So hopefully, at the end of the course, you'll also be able to give a nice technical explanation about what the technology actually is. But let's take a look at how it all started. Because many people think that it all started in 2008, 2009, when Bitcoin came to existence. That couldn't be further away from the truth. The early research, so again, blockchain is a combination of several technologies, and all those technologies have been researched for maybe 40 years. So we can take a look at early research in cryptocurrency and consensus. It started from around 1983, before you had web browsers and before the internet became accessible to the masses. So the first system, or the first cryptocurrency system, is not Bitcoin. The first cryptocurrency system was DigiCash. It came out in 1989, like 20 years before Bitcoin. And as a matter of fact, again, before the internet became widely accessible to the masses, it was actually a relatively large scale, relatively popular cryptocurrency system for that time. What hinders its acceptance, or what hindered its acceptance, was that there were enough users who wanted to use the system, but there were not enough vendors who wanted to sell goods for cryptocurrency. And the system differentiated between vendors and buyers. So, in a hindsight, there was an understanding this differentiation was prohibitive for the development of the technology. And later cryptocurrencies, such as Bitcoin, took the lesson to heart. So Bitcoin doesn't differentiate between different types of users for that reason. In general, Bitcoin is a smart combination of all the development up to this point. But okay, so in 2008, we had a Bitcoin white paper by Satoshi Nakamoto, whoever he is. And in January next year, there was open source release and deployment. So, do you think it was a popular system at first? Someone can tell me what was the cost of a Bitcoin, one Bitcoin at that time? Sorry? Yeah, so you needed, Exactly. It was in that order of magnitude. So you needed like maybe 100 bitcoins to buy pizza, right? Uh, so what happened later? When did it become suddenly popular? So the first sign was when there was a financial crisis in Greece and Cyprus. And what happened is that the bank froze all financial assets. So the people couldn't take money, couldn't take the money and transfer it out of the country, which all the people wanted to do because they were scared of the crisis. And at this point, people realized that cryptocurrency is the way to do it. It was possible to buy cryptocurrencies in Cyprus, and then you can do with cryptocurrency in whatever you want. So this was the first realization that the cryptocurrencies can be actually popular. And this is also when the first academic interest started, right? The first appearance in wide news. So what happened next? The next important development was around 2013. By 2013, so what happened in the period between 2011 and 2013? Bitcoin became widely popular. However, it was not enough. What do I mean it was not enough? It was doing something very specific, but people wanted more functionality. How could we add more functionality? We couldn't do it directly in Bitcoin, so we had to take the source of Bitcoin, port it, do something else, and deploy a new system. And someone else wanted even more or different functionality, yet another new system. So by 2013, we had hundreds of systems spawn off from Bitcoin. And it became a jungle. Basically, people started to lose track of all those systems. And then there came a solution. So Ethereum was the platform that allowed for extensible development. So Vitalik Buterin, the inventor of Ethereum, was talking about the Swiss knife analogy. You know, Swiss knife is a knife with with many sharp ends of different shapes. So it's a single tool which could be used for 100 different things. And that was the idea behind Ethereum. And also at this point, people realized that the same principle so what united those different applications is creation of decentralized trust in an environment where the inherent trust is not present. So around 2013, people realized that there is a paradigm here. And the word blockchain came out. So before 2014, it was just Bitcoin. From 2013, people understood that it's more than just one system. And they started to use the term of blockchain. Yeah, so we had a long history of bubbles and bursts for Bitcoin and for other technologies. We had rapid development of and the emergence of new technologies. And so, for example, in 2017, the word blockchain overcomes Bitcoin in Google searches for the first time. So it was interesting that in India, sort of the interest of blockchain started a bit later. I was told that significant interest came around in 2019. But today, actually, India is one of the leading countries in terms of the use cases. Right. So that might be the reason why sort of the delay in the interest. But on the other hand, when people realize that it's not just about cryptocurrencies, this is where it all started. So what happens today? Blockchain penetration. Many governments in North America, Europe, Asia, coming up with their own blockchain-related strategy and legislation. So I'll talk about EBSI, which is Pan-European Blockchain Services Infrastructure. About more than 40% of top global banks have rolled out some commercial blockchain products. Microsoft at some point declared blockchain as a must-win technology for the business. IBM opened a new department, and there were dedicated labs and education programs in blockchain engineering popping out around the globe. So just some of the universities where those labs and education program originated. And of course, it also became a hot topic at many conferences, whether academic, whether societal, or whether industrial. A couple of words about EBSI. So what is EBSI? So in 2018, 29 countries of Europe, including, well, I'll not talk about the politics of Europe, but 29 countries have joined forces to create a joint European blockchain partnership, where the idea is to build a European blockchain service infrastructure. And the vision is to leverage blockchain for the creation of cross-border services, so that, for example, a diploma or say a vaccination certificate against COVID, against any disease, could be issued in one country, could be put on blockchain, and could be verified in the different countries. Because in Europe there is a lot of cross-country, cross-border travel. So the idea is to use EBSI for public administration, for businesses, and also for individual citizens. I'm going to talk about EBSI in one of the lectures, so this was just a very brief overview. Now, what about blockchain? So if I had to present blockchain in one slide, or blockchain 101, this would be distributed. It's also sometimes called distributed ledger technology, even though the two terms are not exactly the same. So blockchain is primarily a data structure. The data structure consists usually of a chain of blocks cryptographically linked to each other. So I'm going to talk in lecture number 4 about what it means to be cryptographically linked. Each block contains a number of transactions. Could be financial, but not necessarily. Could be any transactions in the broad sense of the word. And the data structure is replicated. So blockchain is formed, blockchain network is formed by individual nodes, sometimes called peers, and every node replicates the data structure. What you can see here in the illustration is the network between the peers. And the structure is very secure. What does it mean? You cannot alter any data which is already stored. You cannot delete any data which is already stored. The only operation which is allowed is to add new data, a new block appended at the end of the structure. That's the only allowed operation. So, and even that operation is not taken easily. In order to append a block at the end, all nodes in the network need to run the consensus, it's like voting, and agree, let's append the block. If they cannot agree, the block would not be accepted. And this is why consensus plays such a central role in the technology. And cryptography and security techniques are used in many places. It's used to encrypt the data, to prevent unwanted modifications, to gain a right to propose new blocks, to execute and verify transactions, and to create the ledger. These are just some examples. So blockchain is frequently compared with distributed databases. And sometimes there is confusion because people are just saying, okay, we could use distributed database or we could use blockchain. Blockchain is a replacement. Actually, that's not precise. There are some use cases where distributed databases are more suitable and other use cases where blockchain is more suitable. So there are two fundamental differences between distributed databases and blockchain, the way I see it. The first difference is that database is an organized collection of data representing the current system state. And the main functionality of the database is to allow efficient data retrieval, fusion, aggregation triggered by user queries. So it's all about viewing the data. In contrast, blockchain represents a ledger which is a history of transaction, or more generally, changes to the system state. So in blockchain, there is not even necessarily a concept of the state. You can calculate the state if you track the whole history of changes, which can be very long. But viewing and querying the state is not the main point of blockchain. So in Bitcoin, there is no such a thing as user balance. In Ethereum, there is user balance. It keeps track of the contract state, but it only provides very limited means to retrieve it, unlike databases. The point of the blockchain is not to query the state and process the data. It's not data processing. It's more data verification. So everything can be verified from the beginning until the end. Blockchain doesn't support query languages, data view, schema, join, and other database concepts. So as a result, another related difference is that Ethereum and other blockchain systems keep the entire history, and the history grows and grows. Nothing can be deleted. So it can become very large, right? It means that usually the storage space in blockchain is much more expensive than the storage space in databases. So you need to be very careful. When you design a blockchain application, you need to think twice what you want to put on blockchain and what you do not want to put on blockchain. You don't want to put data on blockchain just in case. So that's another difference from databases, which are organized to store large volumes of data. So one common technique is to store some data off-chain, but to keep some indexes and some links and some security-related information to verify the correctness of the off-chain data. That you can store on-chain because it's much shorter, much more compact. And there is another major difference between blockchain and distributed databases. And that's the trust model. Distributed databases are usually set by the same organization. So even if the database is distributed, meaning it runs on multiple nodes, those nodes would be overall trusting each other. They would not be expecting attacks from within. And then, so collectively, all those nodes would be providing services related to the database. And of course, the users, the clients, may try to have access rights. So the clients may try to gain access to hack the database, to gain unauthorized accesses. So protection against attack from the clients is a major concern for distributed databases, but not necessarily attacks from within. Now let's compare that to blockchain. In blockchain distributed ledger, the trust boundaries are different. Say in Hyperledger, there is consortium, and each node would belong to one of the organizations. There are multiple organizations in the consortium. Those organizations do not necessarily trust each other. So they need to build the trust. They need to verify information to a much larger extent compared to distributed databases. On the other hand, the clients may sometimes come from the same organizations. So the clients may be even more trusted compared to distributed databases, depending on the setup. But overall, so there are variations here, but overall, the trust model can be quite different. So I see it as the two major differences between distributed databases and blockchain. So let's talk a little more about the terminology, Bitcoin and blockchain. So Bitcoin is a specific system. It's very concrete and specific thing. We know all about its design. There are so many documents. And if something is not documented, there is a reference implementation. So we can look up in the source and get the exact answer about anything we want. There is only one deployment of Bitcoin. And even though, as mentioned, many systems originated from Bitcoin, and many other cryptocurrencies, many spin-offs with maybe just many forks, with just minor differences. But they are not called Bitcoin, so there is no confusion. Blockchain, on the other hand, is totally ambiguous. So it can be the data structure, chain of blocks. It can be the exact data structure of Bitcoin. It could be a separate concept. It could be a guiding design paradigm or principle. There are developing standards, but so far there is no strong standardization in blockchain. So people would say it's a generalization of Bitcoin, but in what direction, right? So in practice, you ask people what is a blockchain, the number of different answers you will be getting will be approximately equal to the number of people you ask. So it's so varied and diverse. There are hundreds of different systems and implementations, and if you take Ethereum alone, so Ethereum, right? There is one major public deployment of Ethereum. But you can also take Ethereum and install it yourself on your computer, with your friends, within your organization. There are also hundreds of proprietary deployments of Ethereum, which you can configure to do something a bit different. So all this creates significant, well, sometimes confusion, but also the need to be very precise about when you talk about blockchain, what kind of blockchain you're talking about. Distributed ledger is a bit more commonly understood. So as mentioned, it's an append-only log storing transactions comprised of immutable blocks of data. It cannot be tampered with. It must be deterministically verifiable, and it's able to execute transactions programmatically. It's fully replicated, and it's decentralized. So it does not rely on a third party for trust. And still, if you look at the literature, you would be finding many different definitions of blockchain. This is an example. So as an example, I'll give you 5 different definitions, and they're all used. Definition 1. It's a system that uses the blockchain structure, exact blockchain structure of Bitcoin, but extend the functionality. So it could extend the business logic. It could slightly tweak, adapt the consensus protocol. Definition number 2, it's a system that maintains a chain of block. Could be a structure other than of Bitcoin, for example, in Ethereum. Definition 3, it's a system that maintains a ledger of all transactions, but not necessarily stored as a chain of blocks. This is the case in IOTA and other cryptocurrency using directed acyclic graph. Definition number 4, it's a system with distributed non-trusting parties collaborating without a trusting intermediary. That's the definition adopted in the Corda system. And definition 5 is probably the most frivolous. It's a system that uses smart contracts. So the last 2 definitions are more about actually how blockchain is used and what it is. Well, the good news is that the people do agree about the main benefits of using the technology. And the main benefits is that it enables parties who do not fully trust each other to form and maintain consensus about existence, status, and evolution of a set of shared paths. And this is its main benefit, so the main feature, the main principle which benefits in blockchain-based infrastructures. And the second main benefit is the ecosystem of smart contracts, about which we are going to talk a lot in this course. So I'm going back to, I'm going to repeat these benefits many times in the duration of the course. So far, this is just a very high level overview. Now we are going to start with the origins with the background on, in this case, on consensus. And in the next lecture, I'll be given a background on cryptographic primitives. So the research in consensus started in about 1982, when basically the following problem was considered. Imagine that you have several armies surrounding the city, and they want to attack the city. If they coordinate their attack, they manage to sack the city. If, however, they do not coordinate well, and only one of the armies attacks the city, the army will be defeated. So coordination, very important. So there is one distinguished process, the commander, which proposes initial value. And the value could be attack or retreat. A retreat meaning let's not attack at this time. Let's attack at a different time. And the other processes, under commanders of the armies, say the lieutenants, communicate the commander value between each other and make sure that they all agree on the outcome, so it would never happen that just one army attacks. What's the problem? The problem actually, like, it has significant historical interest. In the Byzantine Empire, the generals were known for his treachery. So sometimes they would prefer to see the other general destroyed than to attack the city. So they were really malicious, and they could betray the other armies. So they could lie. For example, a lieutenant can say to the other lieutenant, I heard that the commander told us to attack. Well, in fact, there was no such command. What happens? If the other lieutenant would mindlessly attack the city, it would be the only army attacking the city, and the army would be destroyed. So the assumption is that there are Byzantine processes, Byzantine coming from the Byzantine Empire, and there are correct processes for like the good lieutenants who are telling the truth. And even commander can be Byzantine. So what do we want to achieve? Consensus means that if the commander is correct, then all correct processes should agree on the proposed value. And if the commander is faulty, then all correct processes would agree on a value, but not necessarily the value which was sent by the commander. So let's take a look at a few scenarios. This is a scenario with four nodes, of which one can be Byzantine. And the Byzantine node is colored in a different color. Okay, so in this, what happens in this scenario? The node, okay, so the commander would send a certain value V to all of the lieutenants. Okay. Now, this lieutenant is Byzantine. So it would tell, okay, about the notation. 1 means that this is the first round of communication. V means this is the value sent. Okay? So in this case, the commander is honest, sent 1V to everyone. And say Lieutenant P2 process 2 sent message to 1V, 2 meaning round number 2. And the message saying, in the first round, I saw the value of V from the commander. Okay, so this is, P2 is honest. However, P3 is Byzantine. So it will be sending 3.1U to P2 and 3.1W to P4, where U and W are just random spurious values. So in this case, would they reach a consensus? Would the honest nodes reach a consensus? Well, the answer is yes, because each node could look at the majority of the messages it's getting, and the majority would all say V. So the fact that there is one U here would not, okay, so majority of V, VU is still V. So P2 can, based on majority, decide that the value should be V. Now P4 would do the same. So P2 and P4, the honest lieutenants, would reach the same conclusion. And the consensus is achieved. This is the second case, is the case of a Byzantine commander. And here the commander was sending 2 different values. Now, what happens here is that there is no majority. So each process would see that no value is getting a majority. U was only sent by one process, V was only sent by one process, and W was only sent by one process, no majority. So P2 decides on a special value, like a faulty value. And again, all the processes, all the honest lieutenants reach the same conclusion. So that's still a good scenario. Now, this is a case with 3 nodes. So there are 2 different scenarios. In the first scenario, P3 is Byzantine, and the second scenario, the commander is Byzantine. And in the first scenario, let's look at both scenarios and see what P2 is doing. So P2, in the first scenario, is getting the value of V from the honest commander, and is getting the value of U from P3, which is Byzantine. Okay, so there is no majority. The second scenario, the commander is Byzantine. The commander sent different value, V and U, to different lieutenants. However, P2 is not able to distinguish between the two scenarios. In both cases, it's getting V from the commander and U from the other lieutenant. So it doesn't know what to do, which value is the correct one. And thus, consensus is not achievable. So this underlies a major impossibility result. There is a major theoretical impossibility result that if at least 1/3 of the processes of the nodes are Byzantine, consensus cannot be reached. So we can see it in a very simple scenario with 3 nodes, but that result, that impossibility result, can be generalized if at least 1/3 or more of the nodes are Byzantine, no consensus can be reached. The result can be alleviated, mitigated with digital signatures. So if every message is signed, the result doesn't exactly hold. Okay, that's the same scenario, but with digital signatures. So in this scenario, P3 cannot forge P1 signature. So when reporting to P2 about what it heard from the commander, it would not be able to forge to change the value, because the value of 1V was signed. And when forwarding the message to P2, it would also need to forward the signature from the commander, and it's not able to forge the signature and tamper with the message. And in the second scenario, it would be if P1 is the faulty commander, it would send 2 different messages. Both messages would be signed, and if P3 forwards the message from the commander with the signature to P2, then P2 will see that commander actually sent 2 signed messages with different values. And that means that the commander is faulty. So the detection can be achieved with digital signatures. The problem, however, is that in practice, it has been shown that digital signatures cannot always be relied upon. And this is why the strongest Byzantine resilience means that we cannot rely on digital signatures. So this is the end of the first lecture. Thank you, and please ask questions. Um, well, well, okay. Initially, it was a purely theoretical exercise, inspired, however, by the historic evidence. But the problem of consensus was in the early 80s, it was purely theoretical. Yeah, in the lecture on consensus, I'll talk more about it. But yeah, later they tried to verify the result on maybe like 4 different nodes. So in the 90s, like a large scale consensus system would run on 4 servers, right? But this is where it started, and then sort of there was a question of how to scale. In the lecture on consensus, I'll tell you a bit about what Google is doing with consensus-related services today. So it depends which model. Right, so Byzantine fault tolerance is just one of several strands of consensus. Right, so there are different types of consensus. Like this is not the type used in Bitcoin, but this is used in Hyperledger Fabric, for example. This type of consensus. So it's known. Actually, it's able to achieve pretty fast transaction throughput. Transaction throughput can be very high, in like a order of thousands of transactions per second. So much higher than in Bitcoin. The problem of scalability here is actually with the number of nodes, not with the rate of transactions and not with the number of times they're trying to agree. The worst case that could happen is that there is one node which is occasionally acting as normal and occasionally Byzantine and occasionally is delaying messages. And then one of the biggest issue in consensus, in this type of consensus algorithm, is inability to distinguish between a process which became slow for a brief period of time and a process which is inherently faulty. And the process can appear slow okay. So imagine there is Alice, Bob, and Carol. And Carol acts slow. Carol doesn't like Bob, so it acts slow in communication with Bob, but she's very fast in communication with Alice. So now Alice and Bob trying to understand what to do with Carol, or whether Carol should be whether Carol is Byzantine, whether Carol is faulty. So Alice say, I have no problem with Carol. Bob say, I have problem with Carol. So now Alice and Bob would be a discussion, right? And because of this, just to give an indication, because of this, in modern consensus implementation, like the fault detection sometimes may take minutes to be on the secure side. Minutes. So this is the Achilles heel, the weakness of this type of consensus algorithm. But on the other hand, it can achieve much faster throughput. So could you speak up, please? Proof of work? Not related. There are many different types of consensus algorithm. This is not proof of work. I'm going to talk about proof of work in lecture number 5 or 4. Yeah. Sorry, about implementation of what? Yeah, of course. The lecture on consensus is going to give. So yeah. I mean, I'm not able to present all of the cross content all at once in the first lecture. Sorry. But if after hearing the lecture on consensus you still have the question, please ask.